Hello, let's understand principal component analysis for dimension reduction. From the theoretical point of view, increasing the dimension, increasing the feature increases the performance of the model. But practical point of view, increasing the features reduces the performance of the model. For the reduction of data, for the reduction of features, there are various techniques can be used. One such technique is principal component analysis. We'll understand what is data dimensional reduction and what are the various techniques and how to perform principal component analysis and some example in R. The reduction started is data reduction. The original data reduced in such a way that reduced representation of data is smaller in volume but produces the same result. So which is the challenging. And what is data reduction? Why data reduction? The data warehouse databases store terabytes of data. Complex data analysis may take very long time and requires high-end computing infrastructure. Considering this, it is required to reduce the data. There are two types of data reduction: reducing the dimension, that is reducing the number of features. Invalid, less important features, variables can be neglected. So that is called as dimensional reduction, performed using wavelet transform, principal component analysis, feature subset selection. Numerosity reduction means compressing, reducing the data, or it can be done using regression, histograms, clustering, and even the sampling. Now you are all aware of this. So huge data population is not considered for the analysis, where the sample is taken for the analysis and that is inferred for the population, and this is numerosity reduction. Now let us talk about dimensional reduction. Dimensionality reduction eliminate irrelevant. Say I have a data set where some of the columns are not playing major role in predicting or in the data analysis. Such irrelevant data features increases the sizes but which are not important, reducing those features, so reducing time and space required for data mining. This is what dimensionality reduction, and this helps in easier visualization. As I said, there are different techniques. One such technique is principal component analysis. So here it is like this. We have our original data set. This original data is completely projected into the new coordinate system where the dimensionality is reduced. This is what the basic principle of principal component analysis. That is, here we are finding the projection, finding the new projection for the existing data that captures the largest amount of variation in the data. I mean, in the original data, we have the variation. Okay, finding the projection that captures largest variance in the data. The original data here is projected onto a much larger space, resulting in the dimensionality reduction. Here, to perform this, we are going to find eigenvectors of the covariance matrix, and these eigenvectors define new space. How to do it, we'll see. The dimensionality reduction implies information loss, but the PCA here preserves as much as information possible by minimizing the reconstruction vector. So now the question comes, how should we determine best lower dimensional space? The answer is the best lower dimensional space can be determined by best eigenvectors of the covariance matrix. Original data sets its covariance matrix, and the matrix eigenvector, that is nothing but principal components. So finding principal component and then projecting data into this principal component, that becomes the reduced data set. Now, how to carry out PCA? Given data with n dimension, find the k orthogonal vectors. So first step, input data is normalized. Find the k orthonormal vectors. These k vectors are principal components. They are eigenvectors. Here, each data point is the linear combination of the k eigenvector, k principal vector. The principal components are ordered, sorted in the decreasing order, indicating the significance of the strength. Since the components are ordered in the descending order, the size of the data can be reduced by eliminating the weak components. Those with low variance can be neglected so that data size can be reduced. It's a useful technique for exploratory data analysis to better visualize the variation present in the dataset, identifying which samples are similar to one another. The principal components are here the directions where there is the most variance. Indicates the direction which is having most variance of the original data set. To find the straight line that best spreads the data out when it is projected along with. Is a type of linear transformation of the given data set. I mean, we have a original data set. This original data is projected into a new coordinate system is the linear transformation. This linear transformation feeds this original data into a new coordinate system in such a way the most significant variance, whatever the variance there in the original data set, maintaining same level of variance in the new projected data set. Many variables correlate with one another. They will all contribute strongly to the same component, same principal component. Here we are considering two components, eigenvalues and eigenvectors. Eigenvectors indicate the direction. Eigenvalue indicates the value. That value is telling how much the variance there in the data set. The eigenvector with the highest eigenvalue is therefore treated as principal component. Eigenvector with highest eigenvalue, they are treated as first principal component. The number of eigenvalues and eigenvectors that indicate that exist is equal to the dimension of original dataset. I mean, if my dataset contains 9 columns, then there will be 9 eigenvectors and each vector having eigenvalues. So 9 eigenvalues. Okay, let's do this in R. So let me explain the R code. So to perform principal component analysis, we need the function PRCOMP, and this is available in the package FactOExtra. So need to import this particular package in R, then executing the function principal component analysis. And principal component analysis, it works only for numeric data. I'm taking empty cars. So I'll switch to R now. Okay. So I'm taking the empty cars data. So you're all aware of this data set. So our built-in data set having 11 columns where 8 and 9 are the nominal vectors. This I am excluding while doing PCA analysis, and this is showing details of the 32 automobiles. Okay, this is my R code. So we need ggplot also. Then facto extra. So this is to view the cars, and this function here computes PCA. So you can observe here I have taken all the rows and the columns 1 to 7, 10 and 11 because 8 and 9 are the numeric columns. So only the 8 and 9 are nominal columns. I am taking only numeric columns here. So now the principal component analysis is performed. Let's see the summary. So summary here indicates, so there are 9 principal components as we discussed in the theory. Depending on the dimension, how many variables there, those many principal components are generated. And for each principal component, you can see statistical standard variation, proportion variance and cumulative proportion. So mainly here standard variation is taken into consideration. So principal component PC1 is having high variance as compared to, and these values are arranged in descending order. So PC1 in the sense the eigenvector having high variance. So this is in the descending order. If you observe this data set, MPCA data set, it is so PC1 to PC9 for all the 9 variables here given. So it can be understood in this way. Each data point of my original data set is the linear combination of these values of these principal components. If you observe here the principal component 1, so cylinder displacement HP are highly defined here in the principal component, where in the principal component 2, gear and carbonate are having high values. So now let us show this. See the plot, if you observe, this plot here shows eigenvalues, shows the percentage of variance explained by each principal component. So I mean the principal component 1 here showing 62% of the variance. Principal component 2 is showing nearly 23% of variance. So if we take principal component 1 and 2, then around 86% of variance can be shown. So each variable can be plotted like this. So principal component PC along the dimension 1 is PC1 and dimension 2 is PC2. As I said, only these two, PC1 and PC2, these two components are taken into consideration and all the variables are plotted here. So you can observe for HP, cylinder and displacement, the dimension 2 is having higher value. The PC1 is having higher value. So as I explained here. Thank you. You please experiment this. Check it in R. I want you to experiment and check it in. Please check it in R. If any doubt, post it in the classroom.